Yeah, thank you. So I will proceed with the second part of the CORSMAL presentation. Here we have a demo about localization and shape estimation of containers. So here is a problem where we have the views as we saw in the CORSMAL containers of an object lies on a table. And the specific goal here is how can we estimate the dimension in 3D of this object that may be unknown to a system, for example, a perception system or a robot. And by dimension for this type of containers, we refer to height and width. So in order to solve this problem, we propose a novel approach that we call LODE, that stands for Localization Object Dimension Estimator. So here you can see the two views, and we assume that all the cameras are calibrated, so we know the camera poses, and the object lying on the table is always upright and with a circular symmetric shape. So this is one basic assumption that we made for our approach. And the first step in order to localize the object is to find the object in each image individually. For this case, we use a segmentation approach that provides an object mask for each camera individually, for each image individually. And the problem here now arises that the object may be textureless, so it's very difficult to find correspondences between the two views. And we would like to rely on the fact that centroid in the object mask is the most reliable correspondence that you can find between these two views. So what we do is to estimate the centroid for each image individually in the object mask. And then we use projective geometry, especially triangulation, to estimate the centroid in 3D of the actual object. After estimating the centroid in 3D, we would like to estimate the dimension, but to do so, we rely on hypothesis of the shape of these objects. So we hypothesize a 3D cylindric that consists of multiple circumferences that are sampled at different heights, but with a center with respect to the estimated centroid in 3D. So when we have this shape initialization where the circumferences are in the hypothesis larger than possibly the actual shape of the object, we would like to have an algorithm that can fit the real boundaries of this object. So let's go more in detail on what we call here iterative multi-view 3D 2D shape fitting, where we exploit this 3D hypothesis and we verify the hypothesis in the object mask of both views. So for each circumference L, what we do is to sample n 3D points, and exploiting the camera poses and the calibration parameter, we project the points of each circumference in each view, in each image. And then we would like to check a convergence condition. That means that we would like to understand if all the points that are projected in the images lies in both object masks. When the condition is not satisfied, what we do is to reduce the radius of that specific circumference and then reiterate over this process of resampling the 3D points for each circumference, project the point, and then check again the condition. When the condition is satisfied, so all the points of that specific circumference belongs to both object masks, and we do this for all circumferences, we can finally obtain the estimated width and height for that circumference, but also across all the object. So here there are some examples of this iterative approach with some containers from the CORSMAL containers. And you can see how the points lying outside the segmentation mask are shown in red, and when they converge becomes green. And here is another example with transparent objects. And here it basically shows how the approach can roughly nicely estimate the shape of the object, and by product we can estimate the object dimension as well. So in our experiment, we compare our approach LODE with the one state-of-the-art NOx, which is based on deep learning. NOx rely on a single view, but exploit depth data, something that our approach in their assumption won't avoid. So we want just to work with RGB images. We compare also with a baseline that we call SegDD, where we use the segmentation approach of LODE on both RGB and depth data, and we back project the mask using the depth information on a single view. We also compare LODE with the same approach, but apply on infrared image of the CORSMAL containers dataset, where basically the images of the infrared are coming from the same camera in a two-narrow baseline view. So let's have a look at the results of the object dimensions. So when we look at the absolute error for object height, we can see that the median of the error is similar across the method. However, LODE achieved a smaller standard deviation across all the configuration existing in the CORSMAL container dataset. When we move to the absolute error for the object width, we see that actually our approach is very accurate in estimating the width compared, for example, to the state-of-the-art NOx. And again, here, the standard deviation is quite small across all the configuration. Although I would like to point out that all the results here are provided for actually localized objects. So as you can understand, one bottleneck could be the localization part. So let's have a look at the results of the localization. Here there is a video where we use a mask RCNN that was retrained with only 4 classes on the COCO dataset. And you can observe that in some transparent objects, the method fails in finding the object or nicely find the mask in either of the 2 views. And also in some cases, there are some inaccurate masks because the mask was truncated compared to the real boundaries of the object. So apart from these qualitative results, so we would like to quantify the error. So we compute what we call localization success ratio, which is the number of localization over the total number of configuration in the dataset. And we can observe that LODE in this dataset achieve higher localization success ratio. Here are some further results of the shape fitting a convergence for a specific configuration of LODE and on all the containers that we saw in the CORSMAL container dataset. We can observe that there are some segmentation failure for highly transparent objects like the diamond-shaped glass on the left and the beer cup on the right. So it's very difficult for a method like mask RCNN to provide an accurate estimation of these objects. We have some inaccurate segmentation as we saw in the previous slide, for example, for the cocktail glass. So here the mask was somehow truncated. But we have also some inaccurate estimation at convergence of few methods. And in this case, it's mostly related because this object doesn't fit the actual assumption of the circular symmetry in our approach. As a qualitative comparison, we can see here all the methods and how they perform in different settings, backgrounds, lights, conditions for different containers. And we can observe on the right that all the method fails, for example, in this case of a transparent glass with a uniform background behind. Although NOx fail mostly in all transparent containers, and the SegDD provide very inaccurate estimation. So LODE overall is able to reconstruct a shape of most of the container with some inaccuracy in some cases, and also performs for all type of opaque containers, whereas when we use infrared images, this can fail. So I would like to conclude by rephrasing the fact that we propose a novel approach that is called LODE, stands for Localization Object Dimension Estimation in 3D. The core of this algorithm is an iterative multi-view 3D 2D shape fitting algorithm. And the assumption behind this approach is that we are considering objects that are upright and also with a circular symmetric shape. But the advantage of this approach at the moment is that it doesn't rely on any depth data, whereas most existing approaches nowadays are using depth data. Or, for example, they use prior 3D object models, which in our case we don't have. And also we don't consider any marker existing or that can be patched on top of the object. As a feature work, we would like to address occlusions. So in this case, the object were most of the time visible. For example, we would like to address occlusion in the CORSMAL containers manipulation dataset, and also to generalize to different object shapes, like the food boxes, or different object poses. Here is a QR code for you to have a look at the details of our approach loader. And I would like just to say that our this approach was presented at ICASS 2020 this year. Thank you.